Welcome back to the deep dive. Today, we are really cracking open something that's felt like a black box in AI for a while now. It's this kind of magic behind why reinforcement learning, RL, suddenly makes large language models so much better at, well, complex reasoning, think solving tricky math problems. For ages, really, the success of RL just seemed puzzling. Researchers would see these weird things happen, like sudden aha moments, where a model just gets a complex skill instantly, or that phenomenon of length scaling where asking for a longer, more detailed output actually leads to dramatically better answers. It felt almost random, didn't it?
Exactly. It looked like luck. But the sources we're diving into today argue something different. They say these aren't random glitches or separate events at all. No, they're actually clear signs, behavioral signatures of a single, really structured process happening inside the model. So our mission today is to unpack that process.
Yeah.
The claim is RL is forging what they call an emergent functional reasoning hierarchy right inside the LLM. And what's really fascinating is how much this structure seems to mirror, well, how we think, how humans tackle complex problems. Understanding this hierarchy, it turns out, led straight to a new, much more efficient training algorithm. So we'll unpack that architecture and the algorithm it inspired.
Okay, yeah, let's get into that. An internal reasoning hierarchy. It sounds almost like cognitive science, but for AI. So what does this actually look like inside an LLM? This separation of duties, and what's the human parallel they focused on?
Well, the parallel is quite specific. It's that split in our own brains between, high-level strategic planning and the more automatic low-level execution.
Yeah.
Think about your prefrontal cortex figuring out the overall strategy, like which math theorem to apply, maybe versus the part of your brain that just, quickly does the algebra steps or the arithmetic. Very different jobs.
Right. One's the architect, the other's the builder.
Precisely. And in LLMs, the researchers found that RL functionally breaks down the reasoning process into two different kinds of tokens. And they can identify these using a concept they call strategic grams.
Strategic grams. Okay, that sounds important. So tokens are the basic words or parts of words, right?
Yeah.
How do you tell which ones are doing strategy versus just the grunt work?
It really comes down to their function in context. So the first type, high-level planning tokens. These are the big moves, the strategic decisions that guide the whole reasoning process. They often look like logical steps or phrases, engrams that act as one idea. Things like deduction, so we can use the fact that, or maybe branching, okay, let's try this other approach, or even backtracking, hang on, the problem statement mentioned this, those kinds of moves.
Okay, the director shouting instructions.
Sort of, yeah. And the second type is the low-level execution tokens. These are the operational bits, the actual calculations, substituting variables, applying a formula directly, necessary stuff, high volume, but not really strategic on their own.
But hang on, if RL is just about rewarding the final correct answer, why wouldn't the model just learn to value the whole sequence? Why wouldn't it all just average out? Why is separating them so crucial?
Because separating them reveals that the main difficulty, the bottleneck for learning, actually shifts during the training process. It's not static. The analysis showed this really interesting two-phase dynamic. Phase one is all about procedural consolidation. So early on in RL training, the model is basically just struggling to be correct at the low level. Think about it. You could have the most brilliant strategic plan for a math problem, but if you mess up one simple calculation,
The whole thing falls apart, right?
exactly, the whole reasoning trace is invalid. So the model has to prioritize getting those basic steps reliable first. It needs a solid engine.
Okay, so if it's just focusing on correctness, doesn't that sound a bit like old school supervised learning? Just copying correct steps. How is it still RL?
It's still fundamentally RL because the reward comes at the end of the whole sequence based on the final outcome. That overall success failure signal forces the model to quickly lock down reliable procedures. And the evidence backs this up. In phase one, you see a sharp drop in things like relative perplexity and token-level entropy, specifically for those execution tokens. Basically, the model gets much more confident and less uncertain about how to perform the basic steps. It builds its reliable arithmetic toolbox, you could say.
Got it. Builds the engine first. Then what?
Then comes the really interesting part, phase two, strategic planning. Once the model is pretty good at the basics, once that engine is reliable, the learning challenge shifts entirely. Now, the model can execute correctly, so making further progress, getting better scores, it all comes down to exploring and mastering better strategies. High-level planning becomes the new frontier.
And you can see that shift in the data.
Absolutely. You see it in those strategograms we talked about.
Hmm.
Specifically, there's a steady increase in what they call the semantic entropy of those strategograms. That means the model isn't settling on just one strategy. It's actively exploring and expanding its repertoire of different high-level plans. It's diversifying its strategic thinking.
Wow. Okay. That actually makes a lot of sense. It's like learning math in school, right?
Yeah.
First, you drill the multiplication tables, then you struggle with which formula to actually use. And if that's true, this internal shift, this two-phase thing, it finally gives us a real explanation for those weird phenomena we started with.
It really does, those aha moments.
Yeah.
That's likely the observable effect of the model suddenly internalizing a powerful new strategic concept it's discovered. Maybe it learns self-reflection or a better way to handle branching logic.
And length scaling, the longer answers being better.
It's not that length itself is the magic ingredient. It's that more sophisticated strategies, things like careful planning, laying out cases, backtracking when something doesn't work well, they naturally use more of those planning tokens. They produce longer, more detailed reasoning traces because the strategy itself is more elaborate and deliberative. The length is a byproduct of successful strategy.
Okay, so the strategy drives the length, which correlates with success. Makes sense. So if the strategic part, those relatively few planning tokens, is where the real learning leverage is in phase two, then our standard RL algorithms must be pretty inefficient, right? Things like GRPO.
That's the core insight, yes. Standard methods are strategy agnostic. They assign credit or blame pretty much uniformly across all the tokens in a sequence. Imagine like a company has a breakthrough strategy from the CEO leading to huge profits, but the bonus gets split evenly between the CEO and, I don't know, everyone who operated the coffee machine that quarter.
The CEO's incentive gets totally diluted.
Exactly. Standard RL spreads the reward thinly across hundreds of basic calculation tokens and the handful of crucial planning tokens. It just doesn't focus the learning pressure where it matters most for advanced reasoning.
Which naturally leads to a better approach. We need something that understands this hierarchy. Enter HECRA.
HICRA, yeah, pronounced HICRA, hierarchy-aware credit assignment. It's designed specifically to address this bottleneck. It actually builds on GRPO, so it keeps the good parts, but it modifies how rewards or advantages are assigned. It explicitly prioritizes those high-level planning tokens.
How does it do that mechanically?
It focuses the learning signal. So when a reasoning path is successful, HAI Shiri doesn't just give a little reward to every token. It significantly amplifies the reward signal for the strategic planning tokens identified within that path. And importantly, when a path fails, it doesn't hammer those planning tokens too hard. It applies only a mild penalty amplification the paper suggests around 20% or HUB 0.2. The idea is to encourage trying a different strategy next time without making the model totally risk-averse about planning. It shakes exploration towards strategy.
More targeted exploration. And did it work? What were the results?
They reported that, yeah, HFR consistently beats standard GRPO. Across several tough reasoning benchmarks, things like AIM-IS math problems, Math 500, even some multimodal tasks involving vision and language, the accuracy gains were significant, often several percentage points, which is quite a big deal on these hard tests. But maybe the most crucial finding, certainly for future research, was the validation of their measurement tool. It confirmed that semantic entropy measuring the diversity of strategies is a much better guide for exploration than traditional token-level entropy.
Right. You mentioned token-level entropy could be misleading. Can you walk through that again? Why is it flawed here?
Yeah, it's a bit subtle, but really important. Token-level entropy looks at the uncertainty for every single next token the model generates. It's an average across everything. Think about it. In phase one, the model gets really good and confident at the basic execution steps, right? Arithmetic, substitutions. So the entropy, the uncertainty, for the vast majority of tokens, the execution ones naturally goes down. They become predictable. This drop in the majority dominates the average. So the overall token level entropy goes down, making it look like the model has stopped exploring, even if it's actually exploring strategies like crazy.
Ah, okay. It's averaging over too many routine steps, hiding the real action happening at the strategic level.
Precisely. Whereas semantic entropy, focusing just on the diversity of those strategic grams, keeps going up with HICRA. And that high semantic entropy directly correlated with better performance on the actual problems. They even tried boosting token level entropy directly, using standard entropy regularization techniques.
And
It failed. It just made the model more verbose and wishy-washy in its calculations. Didn't improve strategic thinking at all.
Fascinating. So you need the right kind of entropy, strategic diversity, not just random uncertainty.
Exactly. And one last piece of evidence was the error analysis. They looked at why models were failing, and they found RL's main benefit wasn't fixing basic calculation errors. The models are already pretty good at that.
Uh-huh.
No, the big improvement from RL, especially with HI was reducing high-level planning and strategy errors.
Choosing the wrong path, essentially.
Right. A perfectly calculated wrong approach is still wrong. RL helps the model choose the right approach more often.
Okay, this paints a really compelling picture. But you mentioned limitations earlier. What's the catch with HRD?
The catch relates directly back to that two-phase process. HRI really shines in phase 2, boosting strategic exploration. But its success kind of assumes the model already has a decent foundation in phase 1. It needs that reliable procedural engine first. If you take a base model that's still shaky on basic calculations and you push it really hard on strategic exploration with HRI, well, it can backfire. It can lead to unstable training. They saw this in some experiments, particularly with models that hadn't quite consolidated those phase 1 skills yet. HRI didn't help, or even hurt slightly.
So you need the foundation first. You can't skip phase
I
1.
need that reliable engine before you start souping up the strategic navigation system, basically.
Okay, so pulling this all together, what's the big takeaway for you listening? It seems the path to really smart AI reasoning isn't just about throwing more data or bigger models at the problem. It looks like it requires something more like a curriculum, a structured approach that first builds that reliable procedural skill, then specifically focuses resources on mastering high-level strategic thinking. It's targeted cognitive development.
Yeah, it mirrors human learning in that way. Build the foundation, then build the complex reasoning on top.
Which leaves us with a final, kind of provocative thought for you to chew on. The fundamental unit in these RL systems has always been the token, right? The word or subword. But this work found that for strategic learning, the token is too granular, too small.
Hmm.
The real breakthroughs, the strategic shifts, seem to happen at the level of these strategic grams, multi-token phrases like, let's try induction or consider the cases. So, if the reward signals are most effective when targeted at these higher level concepts, should future RL systems maybe move beyond the token? Should the fundamental unit of action, the thing we reward or penalize, be defined as a semantic concept like apply theorem X or initiate backtracking, something to mull over? Thanks for joining us for this deep dive.